Hello, this is James Cook of the University of Maine at Augusta, and in this video we're going to be talking about some of the fundamental elements of bivariate regression analysis. Bivariate is a funny sounding word, but it really just means two variables, one independent variable and one dependent variable, where a dependent variable is an outcome and an independent variable means it's not the outcome. That's all in means, is not. So some other variable and its association with some outcome of interest. What is the relationship between the two? That's what a bivariate regression seeks to explain. And there are certain elements, including a constant, a slope, describing the relationship between those two, and together they create what could be thought of as contingent means, which are average outcomes that vary depending on how the independent variable changes, right? That's what bivariate regression is about. So we'll talk about constants, we'll talk about slopes, and we will talk about the idea of how actual observations deviate from predictions. First, the prediction of just what happens if you don't have an independent variable. You just have an overall mean, an overall average. So how far do the actual observed realities deviate from that overall average for everybody? And second, what happens when you introduce an independent variable that lets those means vary according to the value of an independent variable? What happens when you allow contingent means, averages of outcomes that depend on the independent variable? And when you compare the two, what difference do you get in the total amount of the extent to which you're off, the summed squared error? That creates, in a comparison, a statistic called R-squared, and we'll go through manually how to go about thinking about different averages for different groups, different values of independent variables, and then we will let a bivariate regression algorithm in Microsoft Excel automatically determine that, and we'll see if the two match up. We'll do the same for this R-squared statistic, which is just talking about how much you decrease the amount by which your observations and your predictions differ, how much you can decrease that by adding in an independent variable. Well, enough introduction. Let's join an in-person class already in progress to discuss this subject. What we're going to talk about today is bivariate regression. And there's some strong features of this green book, and there's some weak features of this green book. I think the strong feature of the green book is the idea about the equation of a line and remembering what the equation of a line is. Some of you learned it as y equals mx plus b, and you ask yourself, why do I have to study this in high school? This is why. It's because most of the sciences start from the idea of the equation of a line as a prediction. Of course, on page 7, they are using another kind of notation for it, which is y equals a plus bx, but that's the same as y equals mx plus b. A is the intercept here, b is the slope, and all those lines you drew in high school are coming back either to haunt you or to help you right now, because that's what we're going to be doing with data. The idea of the interpretation of slope and is another strong point in this reading. What is the meaning of slope? And can someone remind me what is the meaning of a slope coefficient in the equation for a line? I'm going to see if that one sunk in from the reading.
Well, I remember this from statistics and from this book. Isn't that where it either goes positive or negative, up or down?
Yes, that's one part of it, Keith. So there's positivity and negativity. A slope can be positive or negative, indicating a positive or negative relationship. But a slope is more than that. A slope is more specific than that. So more specifically, what is the meaning of whatever the number is that is the slope?
Can I give it a try?
Go for it, Suzanne.
Is it for every, I'm going to do a terrible job explaining it, but for every like part that the independent variable does something, the dependent variable will move up in like a ratio? I don't know.
Yes.
Or in like
that is one way to put it. Right. So, okay, we're going to close that. Yes. Let me switch my camera over to the computer and let's do a little writing. So, if here we are in Microsoft Word. Okay, we're going to make it nice and big. So you probably learned the equation for a line as y equals mx plus b. To complexify it, they just used different letters on page 7 and said, no, y equals a plus bx, which is the same, by the way, as bx plus a, which is the same as mx plus b. It's just switched around and they're using different letters, okay? So, in both cases, doesn't matter how you write it, there's this italicized, bolded bit here called either m or b, and that is the slope coefficient. Okay, y is, what is y in this equation? Somebody just call it out.
It's the value, the number.
It's actually not a number. You'll get a prediction out of it. You'll get a number.
Is it the line?
Well,
Is it the
this
variable?
whole thing is, it is a variable. This whole thing is an equation for a line. Is it the independent or the dependent variable?
Dependent?
Correct. And let's take a look at that. And just as Isaiah said, it's a variable. Then Keith called out, it's a variable. It is the dependent variable. I don't know who called that one out, but yes, you got it. So if you think about what this is saying, it's saying, hey, there's all this stuff over here that tells us how to predict something. What do you predict? You predict an outcome. That thing over on the left is the thing that you're going to get at the end. That's the thing you want to be able to predict. And that is the outcome. That is the dependent variable, which makes x equal to what?
The independent.
Independent?
Correct. Right. And an independent variable, let's remember, is just a thing that you can measure that has different values. Those values vary. So, this b here, okay, and let's use the book's nomenclature, okay, if that's the equation for a line that is going to predict a value of y based on, it's going to say there's some constant there. A is no, I don't want it to be there, just like that. A is, it's a constant. It is also called the y-intercept. It's just a number. And it tells you when x is 0, what does y equal? Okay, and then we'll figure out b in a minute. How do we know that means the value of y when x is 0? How the heck do we know that? How do we know that a is the value of y when x equals 0? Well, let's take a look at y equals a plus bx. What happens when x equals 0? When you put these two together, what operation is implied when you put two letters together?
You're multiplying them.
You're multiplying them. So this is really the same as a plus b times x. And when x equals 0, what's anything times 0?
0.
Right. Y equals a plus 0 when x is 0, which is the same as saying y equals a. So this whole thing that we were taught when we were kids, that the a is the y-intercept, it's the value of y when x is 0, it's not just like a magician came and made it up. It's what the equation actually means. In order to figure out what a means, all you have to do is plug in a particular value, and then you'll get y equals a. It is what happens when everything else in the equation is set to 0, which is when x is 0. Okay, so there we go. It's just what happens when you put a 0 in as x. It just turns into y equals a. So b. Suzanne, you said it just about right. It is, if we look at bx again, then we have to think about, well, how do we not make bx equal to 0? How do we just make that thing equal to b itself? Any ideas about how to turn bx into just plain old b?
Can you divide it by x, Professor?
You could, but there's something a lot simpler and a little bit more intuitive that we can do. How can you make
Times
when
0?
is no bx?
Do you times it by
Anything
a negative number?
No, it's a positive number. You guys are getting closer. It's not 0. How do you make, what I'm asking is, when does bx, I hate Microsoft Word now, become b? When does it just become b? And this is a multiplication. There's another hint.
You plug 1 in for x.
Yes. When x equals 1. That is exactly when. So, when x is 1, okay, y equals a plus b. So when that happens, b is the amount that y goes up by when x is 1 rather than 0. How much does y go up? When b is 0, right? Y equals a plus, we already established this, b times x, which equals a, because this is 0, right? Excuse me, when x is 0. When x is 1, this is just mathematics. Y equals a plus b times x equals a plus b. What is b? B is the amount that y goes up when you have a 1 unit increase in x. And check this out. Okay, watch this. This is amazing. What if x is 2? Then y is going to be a plus b times 2 equals a plus 2b. Oh, look at that. B is the amount that is different, is the difference when x goes from 1 to 2. Because what is the difference between a plus b and a plus 2b? It's just another b. When x is 3, y equals a plus b times 3, which equals a plus 3b. What does b mean here? B is the amount by which y is going to go up when you have a 1 unit increase in x. Doesn't matter which unit increase it is. We could just do this forever. When x equals 4, y equals a plus b times 4, because that's what x is, equals a plus 4b. Oh, lowercase. And on and on and on. No matter what value x is, b is always the amount by which y goes up when you increase x by 1 unit. Okay, is the comparison of y versus equals a with some y equals a plus bx. In fact, you can think of it like a contest, okay? Which one wins? And by wins, I mean which one better explains, or a better word, better predicts y, and by how much. To figure out that contest is to figure out, hey, if we have some variable x, something, just to remember what variables are all about from earlier in the semester, something we can observe about the world, some characteristic. Does it help us predict y, which is something else we care about in the world, like, does someone die or not? Or how long does someone live? Or do they make it through school or not? Do they graduate or not? Or do they develop a disease? Or do they become a terrorist? Or whatever else you are studying in your literature review. Most of the pieces of work that you are going to be looking at in your literature review are asking, what is it about this thing we care about, this y, this dependent variable? What are the things that make it change? Because if we can figure out whether we can do better than just this equation, whether we can introduce some x in there that helps us understand y better, then we can know what to do to make y change. We can know what to do to keep people from dying. We can know what to do to keep people from getting hungry. We can know what to do to keep people on the road to graduation. We can know what to do to keep people from attempting suicide. We can know what to do to increase their longevity, their life expectancy. We can know what to do in a community to decrease food insecurity. All those things that you care about, and you have something to care about because you're doing your literature review. We're desperately searching for these BXs, something that has some kind of an effect on that Y, something that's just better than this. In order to clarify what that means, I would like to go through, we're going to use a spreadsheet. Yes, we are. Okay, and we're going to make the whole thing bigger so everyone can see it. Okay, so we're going to look at a spreadsheet, but we're going to look at a spreadsheet that is predicting something pretty simple. If you just Google, and you can repeat this at home, you Google voter turnout in the United States and data. One of the first links, in fact this time, the first link is voter turnout data by something called electproject.org, the United States Election Project, in which the dependent variable, let's make this bigger so everyone can see it. That's pretty big, is voter turnout. That's the thing they want to explain. It's all about voter turnout. Here it is again, voter turnout, voter turnout, voter turnout, voter turnout. It's clearly what they're interested in understanding. And look, they have a complete time series from 1787 to 2016. Let's click through on that and figure out what that is. Okay. And then they're going to have turnout rates, and where's the data? Oh, there's a pretty picture. Okay, and that's of turnout rates from 1789 to 2018. There it is, 1789, and there's 2018. Oh, and they have these pretty lines in there. Blue lines and orange lines. And these are all the observations. And, oh, this is the part where I get really excited, because you can download the data. And that's exactly what we're going to do. We're going to download that as a Microsoft Excel document, and we're going to open it up. So let's pretend, and for some of you this may not be very hard, because maybe that is what you are, but let's pretend everyone in this room is a political junkie. And let's make these things really big. Okay. Okay. So we've got columns. Each one has a different, each one has a different number or something to it. We've got a set of headers. Is this a good data set? Does anyone see a problem with it right now? I can see a problem with it.
It's not lined up.
Yeah, what do you mean by that? How is it not lined up?
Everything's not to the far left of the page.
Oh, well, we could do that. There.
Okay.
Okay, but there's still a problem with it.
Everything's not sorted from the least to the greatest.
That's right.
Yep.
As a matter of fact, check this out. There are 2 values of year in here. There's it's the year is 1789, and then it's 1790, and that's in the same row. And remember, one of the rules for a data set is that by gum, there should be just one case for every row. Here there are two cases. That's one case, and that's another case. Oh, darn it, what can we do to fix that?
Well, also, one thing also that's also listed there too is the fact that they've got essentially two data sets. The left one there is for the VEP turnout rate for the presidentials, and the one on the right there is for midterms.
Yes, that sounds like Shannon. Is that right, Shannon?
That is correct.
Hi, Shannon. Bingo. And that's a problem. Okay, so it looks like there's almost two data sets side by side. One saying, oh, hey, these are all the presidential election years, the years in which a president was elected. And then over here are all the years where it was a midterm election, where there weren't presidential elections, but there were, like, congressional elections and things. Darn it, darn it, darn it.
Aren't you going to have to do two separate spreadsheets? Or just put one below?
We could do that. What else could we do? How could we combine these?
Can't you go through and, I was going to say, can't you go through and indicate, okay, the average turnouts between the presidential and midterms for each of those respective years? Because, I mean, even though I know that the years are respectively different, you can go through and still get an average for that time frame.
Right. And in order to do that, was that Shannon again?
Yep.
Yep, okay. So in order to do that, it's like they've combined two variables into one. They're giving us a VEP turnout rate, which is, by the way, the VEP stands for percent of voter eligible population, which, by the way, in 1789 does not include slaves from Africa or of African descent. It does not include people who don't hold property. It doesn't include women. Right. So that voter eligible population is a VEP that's important to understand. So it's measuring two things. It's measuring the voter eligible population. That's the percentage here. And it's also saying, oh, and yeah, this is a presidential election. That's two variables in one column, which is like another violation, right, of the way that a setup is supposed to be. So we can solve that by, let's solve that by adding a column here. And that column is going to be, I'm going to call it pres, just to keep it short, because boy, they get wordy with their variable stuff. And that is it a presidential election year? And for 1789, we know, is it a presidential election year? This isn't a trick question.
Wasn't it? Yeah. Wasn't it George Washington?
And then 1792, is that a presidential election year? It says it is right here. So we can say yes for all of these ones. And we can just, these are all presidential election years. You can know it because you're a student of history. You can also know it because, hey, by gum, that's what this column tells you. Whereas over, yes, sir.
Excuse me for asking a silly question, but you put one there because there has to be a number there instead of just a yes or a no, right?
That's right. Ones are yeses and zeros are nos in data sets. So once we've done that, we don't need to know over here whether this is US presidential or not. We have that information. So let's turn it into something a lot simpler. That's the VEP turnout rate. Now we have two variables. We can do the same thing over here. Is this a presidential election year? This year over here? Oh dear. There we go. Is 1790 a presidential election year?
Yes,
Okay,
it is.
Isaiah's given me the no. That's right. We know all these ones over here are not. And we can go through the 1900s. My grandmother was born in 1901. I was born in 1971. Woo, just like yesteryear. Okay, and here we go, 2018, the last congressional elections. We know from history, right? That was not a presidential election year. 2016 was. And that means that this turns also just into VEP turnout rate. Oh, guess what? Now, these two columns and these two columns are equivalent. Which means we can do what? We can take this stuff. Oh, and year has an equivalent meaning too. And we can just stick them in right here. And now all of a sudden, we've got a simple data set that actually is taking the format we want. It's given us the year, and there are lots of years in there. It's giving us the voter eligible population turnout rate, and it tells us, was this a presidential election year? Okay. And so what? So what does that tell us? So why should we care? Let me turn this back on so I can see everybody. Let's talk about that for a minute.
Well, if you're running for office, oh, I'm sorry, were you wanting feedback?
No, yeah, that was not a rhetorical question.
Yeah.
Why do we care?
Well, if you're running for office, you're going to want to know who should you target and who's eligible. Like if you're a campaign manager or something like that, or you want to see the trends in voting.
Okay, just if you're interested in trends in voting, why should we care what percentage of the voting eligible population turns out? Why would somebody care if turnout is high or turnout is low?
Well, you can look at last election and see how big of a how many people thought about that. 51 million people didn't vote in the last election, and look what happened.
Okay, so we can start to think of general ideas. This is not like number stuff. This is like what we care about. Elections have consequences. And we don't have to say in this room like which presidential candidate we liked or didn't like, but there are a lot of people who have opinions about our current president, just like there were a lot of people who had opinions about the president who came before him, and a lot of people who had opinions about the president who came before him.
Professor?
And hang on, let me just finish my sentence. And so, if you care about who's in office, and you care about whether people are turning out for elections as a sign of interest and participation in democracy, well, you'd want to know what predicts high turnout years and low turnout years. Okay, yeah, Keith, go ahead.
No, I wasn't taking any cracks at anybody, but I was just mortified when I heard the people during the election night talking about how many people just sat this one out thinking that, oh, it doesn't, my vote, 51 million people thought their vote didn't matter. And look what happened.
Okay, so elections have consequences. Getting people to turn out is something that you might want to predict. If you were an election worker, if you were doesn't matter whether you're Democrat or Republican, if you're working for a campaign, you want to be able to understand these patterns. Okay? And you want to be able to say something about the general trends. Is turnout getting worse? Is it getting better? What's going on with that turnout? So in order to do that, what predicts the turnout rate? Okay, So that makes VEP, let me turn the camera back over. That makes VEP turnout our dependent variable. And so what makes voter eligible turnout, voter eligible population percentage turnout go up? What makes it go down? We have a couple of possibilities here, right? It could be that the best possible prediction is just some number. Maybe we'll call it A. It's a constant. Maybe that's the best we can do. Or VEP turnout equals some number plus the effect of something else. And it's a contest. Can we introduce an independent variable that will help us understand turnout better? So let's start with this idea. The idea that voter eligible population turnout is just on average equal to some number, that that's our best prediction. If you wanted to make a prediction about what voter eligible population turns out to be, what's your best guess based on history? How would you just come up with one number that would make the best prediction?
Average.
The average, or the mean.
I beg your pardon?
The best guess, I'll write this out, the best guess for a dependent variable.
Independent variable?
For your dependent variable is the mean if you have nothing else. Oh gosh, and there we go. The best guess for a dependent variable is the mean if you've got nothing else. The best guess for what it's going to be in 2020 is the average of what it's been before. And we can literally do that. Let's calculate the average. The average is, for all those years, wow, 116 years of elections. My goodness, that's a lot of elections, federal, national elections. That average is 53.2. 53.217 for all those years. The mean equals 53.217. Let's change that. 53.217. And if you've got nothing else, that means A equals 53.217. And that means if you've got nothing else, VEP turnout equals 53.217. That's your best guess if you've got nothing else to go on. You've got no other independent variable. Okay? So let's make a picture to talk about what that looks like. Because right now I've just been talking about numbers. Let's make a picture. Let's take this data, let's sort it out by year, and then let's look at the voter turnout rate in a pretty picture. Okay, by creating a graph, a scatter plot. And that is VEP turnout, y-axis. Oh, look, y-axis, it's the y by year. Huh. X. Let's make that bigger so you can see what I'm talking about here. Okay, so there's our pretty picture. That's actually the values. That's all this stuff on the left. So if I roll over, I can get little values here. Like this is telling me in 1818 it was 41.1. In 1840, voter eligible population turnout was 80.3. And if I'm telling you that if you have no other information, that the best guess is that VEP turnout equals 53.217. What I mean is that no matter what else is going on here, say by year, or by whether it is a presidential election year, that voter eligible population turnout is going to be equal to 53.217. That prediction looks like a line. So let's put in a line. Let's see. How can I do that? How can I put in a line? Ah, right there. Let's put in a line at about 53.217. That's about right there. Let's draw that line. Let's make it flat as possible. And then let's change its color.
Can you make it thicker?
And make it thicker. There we go. How's that? That is what the line y equals, or VEP turnout equals 53.217 looks like.
The trend doesn't look like it's going to be too good in the upcoming years, does it?
That's the observation I was looking for. Does that look like it fits what actually is going on?
That's exactly how Ms. Blanca taught it.
Well, did she use voter turnout?
No, but we had to do we had to do linear regression and all that.
Well, then maybe we're going down, barking up the same tree, but never hurts to do it again. So, how much is it wrong? How much is it off of all these little dots? Well, we don't rightly know. But
what are the percentage points?
But we can find out. Okay, this is my question. How much is the prediction line, y equals VEP equals 53.217, off from where the actual dots appear? How much is this off by? Well, to measure that, we can actually do a measurement of it, right? For each of these dots. We can figure out what the prediction is, right? So what's our prediction based on just the mean. No matter what year it is, what does BEP election turnout rate turn out to be, according to our average?
53.217.
53.217. No matter what the year, that's what that line predicts. It's a pretty basic prediction, right? And actually, I'm just going to turn that into VEP voter turnout so we can stick those guys closer together. Well, how much does this deviate from that? We can literally call it a deviation. And what a deviation is the amount by which it's off. So we could literally just take whatever is in cell B2 and subtract C2. And it tells us, oh man, that dot is 41.617 points lower than our prediction. The next year, we can do the same formula. Oh, and that one's 31.617 points off because it went up exactly 10 points. And we can do that all the way down the line. And for some years, wow, 1814, that's pretty close, only 0.4 points off. And for other years, 1824, yeah, it's really bad. 1820, it's off by 43 points. Oh, we can keep going. And we can get a sense okay. I'm just going to actually, rather than cutting and pasting, I'm going to just do a quick cut and paste by clicking on that little square and dragging it down all the way up to 2018. It's going to tell us by how much it's off. Okay? So that's telling us what direction it's off by. Here's a neat truth. If you want to look at the total that it's off by, if you want to add up all those deviations, it actually adds up to essentially 0. That's what these deviations do. The reason it turned out to not be exactly 0 is that the average is not exactly 53.217. It's actually 53.21724,138. So if I had included that, the actual sum of all those deviations would end up being 0, which is one way of saying it's the best prediction if you got nothing else. How can we get one number that tells us about the magnitude of the deviation when we've got some that are negative and they're canceled out by some that are positive, which you can see by looking at this here. Sometimes there's a negative deviation of those dots from the line. They hang down below. And sometimes there's a positive deviation. They hang out above. If the positive deviations and the negative deviations just cancel each other out, we just can't add up all those deviations and get a measurement of the magnitude of it. How can you measure the magnitude of that deviation? There are a few ways to do that. Anyone got some ideas?
Find the average of the deviation.
Well, if you take the average of that deviation, you also get 0.
Well, what if you have the absolute value?
Oh, you could do absolute value, right? If you took the abs, that's the absolute value of D2, the absolute value of that, the magnitude of that is 41.617, and so on and so forth, right? That's one way to get rid of the sign. and then you could just take the sum of all that, B2 to B117, or E2 to E117. Oh, and then you actually get a number. Like the total amount, if you take away the pluses and the minuses, right? Wow. And you get the magnitude, it's like a total of 1,525 points off all across that graph. That's one way to do it. It turns out, for complicated reasons, that statisticians don't like to use absolute values. So we're not going to do that. But you could. Statisticians like to do something different. They like to square it. And the neat thing about something times something, if it's a negative number times a negative number is a positive number. And a positive number times a positive number is also a positive number. So, for complicated reasons I'm not going to go into today, rather than doing absolute values, which Isaiah is totally legit, okay? Statisticians like to square it instead. And so you get a nice big juicy fat number. But they're all positive numbers. Look at all those numbers. They're all positive. Sometimes, like over here in what year? 1814, when that negative number is just 0.417 off, the squared amount is also going to be low. And sometimes when the number is big, doesn't matter if it's positive or negative. Like, let's compare these 2 years. 1840, you square 27 and you get 733. Negative 26.3, just a little bit less. But a negative number times a negative number is positive 692, indicating that both those years are off by a similar amount. Similarly, 1826, the prediction is off between these two lines, columns here, by just negative 3.117. And so the squared term is kind of small. In 1830, the prediction is off by positive, that is, the actuality is higher than the positive number, by 2.43, and that gives us a small squared number, okay? So you could do the same thing, and that's exactly what statisticians do, to get rid of the sign of how much you're off by. They square the deviation instead. Squared deviation. And the total amount, hang on just a second. The total amount at the bottom, just a second, Keith, is E2 to E117. And that is called the sum squared deviation. Or sometimes you'll see it called the sum squared error, because it's the amount you got off. You're wrong if you guess 53.217. Every time you guess 53.217 for any year, you're off. You're off by a particular amount, and that amount, the magnitude, is described by its square, because it takes off the plus and minus. And you add that all up, and sum means just you add it all up, add up all the squared deviations, which are also squared errors, and you get that number. And that's what it is. Keith, go ahead.
Thank you. Thank you. That's all I wanted to know.
Okay. Oh, was that your question?
Yep, that's all I want to know.
Great. So for this particular sum squared error, it is a particular, or deviation, same thing, it's just synonyms. It is the sum squared deviation for when we only use the mean. It is the sum squared error, that's a synonym. It just means the same thing. You'll see it referred to as both when we're only predicting based on the mean. The mean is 53.217. We are creating in pictures a prediction here that is telling us, hey, look at that, man. Yeah, never mind all that squiggliness. We think it's just all the way across going to be 53.217. And that's giving us a lot of sum squared error. The next question is, and I'm going to wrap that right away so we can look at it. There we go. The next question is, can we reduce that error? Can we reduce the error by adding in an independent variable? If so, we can understand the universe better. And statistics, scary math sounding word, tells us what the universe is. And that's what we're doing today. So let's go back to, what do we know so far? Okay, we know that if we're wanting to predict Y because we care about something, like let's say we're a political operative and we care about voter turnout because we want to run elections and have our candidate win, or maybe we just think that democracy lives and thrives according to how much its people participate, which is highly variable over time. How do we know it's variable over time? Because we can scatter plot it and we can notice it goes up and down. Wow! How will we know what happens next year when literally, look at that range of, oh, you can't look at anything. Let me stop mid-rant. Let's turn on the camera. Okay. Phew! Okay, continue rant, because look at that graph. If you look at the blue dots, boy, turnout goes everywhere, from less than 10% of the voting eligible population turning out to more than 80% in 1876. 82.6% of eligible voters actually turned out and voted, and then lately somewhere in the middle. Wow, that's kind of cool. It goes up, it goes down. What will happen next? How do we know? If we care, you know, we want to come up with a good prediction. But, important question, how can we get a good prediction? Well, the first best prediction is just the average. When we predict based on the average, just to continue reviewing, and the average is 53.217 across all years, we end up, look at that picture, we end up being off by some amount all the time. Sometimes, just it seems by chance, we kind of hit the mark. There are a couple of blue dots that are pretty close, but a lot of the time we're really off. Now, let's be fair. When I say that if you have nothing else, the average value is the best, it means that the actual total amount of squared deviation that you get is the best when you have a prediction that is the mean. Oh, now, we could go and we could predict a different amount. Let me show you that that's the case. Let's create another, oh, come on. I just want another line. Can't I do that? Okay, I'll put another line in here. Let's come up with a different prediction. Let's predict that voter turnout is 80. And let's make that nice and green, and let's make it big and thick. Big and thick. Okay, so why don't we just predict that value? Okay, well, we could, and we could do the same thing that we did before. Okay, in fact, let's do that. Let's create 3 new columns in which we do a prediction that is not based on the mean, but it's a prediction that says, yes, voter turnout is going to be 80% each year. Well, our prediction, if we predict that it's going to be 80 each year, is going to be 80. That's handy how that works. And it's going to be 80 no matter what the year is. So just like we had a prediction of 53.217 before, which was the mean, we could just say, yeah, I predict it's going to be 80, right? How are we doing with that? Well, we could do the deviation. We can calculate the deviation for any value. And let's do that. So that is going to be equal to B2 minus C2 again. And this time it's 68.4 points off. Okay, and then we could do all those deviations. Okay, and then we could square the deviations. So the square of that is simply D2 times D2, and then we could do that for each one of these values, squaring each one of them. And then we could add that up, equals sum of E2 to E117. And that number, well, let's put a comma in there, is 114,468.38. And it is the summed squared deviation for 80, or the summed squared error for the value of the prediction of 80. And notice what is different. It is bigger than the mean. Over here, it's just 31,251.71. Here, it's like nearly 4 times as much. That is a worse prediction. 80 is worse. It turns out, try this at home, that every time you make a prediction that is different than the mean, you will do worse. The summed squared error is its lowest when you're just predicting any one number, just one number, right? Whenever you're predicting a flat line, the mean is going to come up with the least amount of total error, which is what summed squared error means. It's the summed magnitude of all that error, and it is its lowest when it's at the mean. You can try this at home. And I suggest you do that. That would be cool, right? You could play around all day. Oh, check it out. We could do this. We could change this. Let's change our prediction to like 40. We could do that so quickly. It's going to change everything. Woo! And we could change all the values. We could do this all day. We could change that to 40. We could make sound effects like I just did. Oh, 40 didn't work out. Well, it's better than 80, but it's still worse than the mean. That's what I mean when I say the mean is the best. Well, what if we go up to, 50? Okay, let's do a prediction, I can't type. Let's predict of 50. Is it going to be better than the prediction for 40? Let's see what happens. Yes! Notice how it gets closer here? It's getting closer now. That's because this is 50 is pretty close to 53.217. But it's not going to get all the way down to 31,259.71 until you hit 53.217, which is the mean. It's going to get you the smallest amount. Look, if you overshoot and you get to like 56 or something, I don't know, I'm just picking a number that's a little bit off on the other side of the mean. Prediction 56. I'm just playing around to show you that the sum squared error, ooh, it's really close now, but it's still lame compared to the mean. The mean is still the lowest amount of sum squared error that you can get. And this is a general truth. I'm showing it to you right now, right? We could make other cockamamie predictions that go all over the place on this graph. We could predict it at 80, we could predict it 40, we could predict it 50, we could predict it 56, but really, if we want to get that error down to its minimum, we want to hit the mean. Any other prediction that is going straight across is just going to oh, I don't know. What is the Easter term? Suck eggs. Okay? It's not going to be as good. So this is our best prediction so far. Okay. So that is kind of summing up where we've been and what we've learned. And I want to go a little farther, but let me pause right now to ask for questions for people who are coming close, who are kind of getting there, who are wanting to know more. Oh, hi Sam, I didn't see you before. Now I see the corner of your head. Nice to see you, Sam, today. So, let's think about contingent means. The overall mean is the average for everything. If that is what an overall mean is, what is a contingent mean? We talked about this a little bit before the exam and a lot after the exam. Who can refresh my memory?
Wasn't contingent meaning that it was the average based on more than 2 variables? No.
Yes. Different
okay.
averages for what?
For different ranges of x.
Yes. Different values of x, and when we say x, we really mean the what variable? Independent variable. Okay. So this is the jackpot right here. This is what, to answer your question, Shannon, multiple regression is all about. Today we're just going to do what's called bivariate regression, which is simpler, which is just about one independent variable and one dependent variable. Okay? And we're going to get more complicated next week. But just imagine that we could get a better mean. Now let's go back to the version of that chart, which, by the way, is showing the same dots as are shown here. They're the same dots. They're even kind of the same color scheme. Probably made in Microsoft Excel, right? But check it out. Those same dots now have 2 colors based on whether it is a presidential election year or a midterm election year. It's almost like these folks are saying, hey, midterms have a different pattern than presidential election years, right? If that's true, then it's like, well, we could have 2 different means. We could have contingent means. One if it's an election year, and one if it's a presidential election year, and one if it's not. We could do that manually. How can we, in a spreadsheet, without doing any fancy schmancy manipulations, let me delete some of this prediction stuff over here. Okay, let's simplify again. Here we are. Okay, we've got year, we've got voter VEP turnout, that's our dependent variable. Here's Prez. What can we do to figure out 2 different means, one if it's a presidential election year and one if it's not? What would you do if you were in command of this spreadsheet? Any suggestions?
Organized by the value of Prez.
Yes. Did everyone hear Isaiah? Try organizing by the value of Prez. Let's do that. Let's make sure we have, let's get rid of all our extra material down here. Okay, so now we've just got a data set again. Let's sort these. Go to data and sort, and let's sort by whether it's a presidential election year. I just did that. Look, so we've got all the zeros on top and then all the ones. Oh, where does it change from 0 to 1? Okay, at row 59. That's row 59. And then starting on row 60, it's 1s. So now I can calculate the mean when it's 0, and I can calculate the mean when it's 1, which means when presidential election year is 1. Ooh. And what is it? What's the marker again where it shifts? It's between row 59 and 60. Okay, 59 and 60. So I can literally say, hey, let's calculate the average for voter turnout. That's column E. Let's do that when it's 0, which is row 2 to row 59. And then, wait a second, that's not right. Oh, that's the deviation. B, voter turnout, is actually our variable. Phew. Okay, which is the average of B2 to B59. That's a little better. And now let's calculate the average of column B, which is our voter turnout variable, when it equals 1, which is the average of B60 to, oh, when does it stop? B117. B117. Oh, cool. Okay, I'm going to take this information over here, and I'm going to put it over here in a special place, okay, so that we keep it. Oh, that's so neat. Because what that is telling me, that's the mean when it's what? Mean when it's 0 and the mean when it's 1. That's contingent means. That is super cool. It says, depending on the value of your independent variable, something else is going to be different. Okay? Okay. Wait, let's check this out here. Okay? So, we had, for 53.217, right? We had deviations, then we had squared deviations, and then we had, if we added all those up, E2 to E117, we had this thing here called the summed squared deviation, also called summed squared error. And that is for 53.217, right? Can we get lower than that if we have contingent means? Let's find out, okay? This is where we're headed. 1, 2, 3. We've got 3 columns to do this bit, and we're going to do it for prediction. And it's no longer going to be for the mean, it's going to be CM for contingent mean, and not for centimeters. And we've got pres equals 0 over here, and our prediction when pres equals 0 is going to be, oh dear, what is it? It's going to be that it's 49.128 if we round up, okay? So 49.128 if we round up. And it's going to be that way all the way through row 59. Ha ha ha. And then, and I know that because I remember, because see, that's where it shifts from 0 to 1 for pres. And then when pres equals 1, which is everything else, we're going to predict that it's 57. Wow. 0.307 is going to be our value. 57 point, that is a big difference. 307. It's a difference of like 8.2-ish percentage points just from one variable. Okay, let's see if that's our prediction for every time it's a presidential election year. And that's our prediction now. 57.307. Now, let's calculate the deviation. And that is going to be B2 minus C2. Oh, check it out. That's a little smaller. And we can take a look at each one. It's like a contest. This is where it gets fun. Oh, that's smaller than that one, and that's smaller than that one. I like it. Oh, they're all smaller. I'm excited. Let's keep going all the way down. And instead of looking at comparing each one and saying, oh, is that smaller? Oh no, see, that one's bigger than that one. But that one's smaller than that one. I could do that all day. Instead, what I'm going to want to do is I'm going to want to square the deviation so that we can look at the magnitude of the deviation. So that's d2 times d2, right? And then I'm going to bring that down, and we're going to look at how much like total squared deviation there is here, and then we're going to add it up, and we're going to see if it's better. What makes it a better prediction? This is the holy grail of prediction. It's a better prediction when the amount by which we're off is less, right? That's what the sum squared deviation is going to tell us. If we add all this up, moment of truth, is it going to be less than 31,259.71? If so, we have a better prediction. Sum B2 to B117. No. Oh, I added up the wrong one. It's the sum of E2 to E117. Oh, and I have to put an equal sign there. I'm sorry, I'm stringing you guys along. Okay, here we go. Oh! Now that, put in a comma so you can look at it. Everyone should be able to read this. Can you guys read the numbers? Give me a thumbs up if you can read the numbers.
Yeah, it's less.
Suzanne, you can read them? Okay, good. They're big enough? Good. That is less. The summed squared deviation for contingent means is less. The summed squared error, the amount by which we're wrong, is decreased. We just, by adding this one variable, did something really cool. We increased the accuracy of our prediction. And furthermore, we can quantify how much we increased the value of our prediction, right? By how much we decreased error. How much of this error is left? Well, to do that, you want to calculate something called R squared. Okay? So, in order to do that, we could just calculate a percentage, right? How much error is still left? Well, that's the error that we've got still left over out of how much that was there if we just looked at the mean. 31, oh, let's not do commas, 29319.57. And let's divide that by 31259.71. And then if we multiply that times 100, which you do to get a percentage, that's our way of saying 93.7, okay, or 0.79% of error is still there. Wah, wah. That sounds kind of sad, but if we take 1 minus E122, that'll give us the amount of error that we took away. And then we could multiply that times 100, and that tells us 6.21% of error was removed by adding our variable. Which variable? Pres. Okay, and what that is, right there, 0.062, or multiplied by 100, 6.21%, essentially. That's the amount of error you removed. That is the thing that they're talking about in your reading. La 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 la. Page 17, everyone. Heading, coefficient of determination. Points 17, 18, 19, all the way to 20 at the top. So all those 4 pages are talking about this. That is our superscript squared. R squared is that number. Multiply it by 100, and you get the percentage of error you remove by adding our independent variable. And it tells you how good that independent variable is now at improving upon just the mean. That's what R squared is. It tells you how much better your prediction is if you introduce your variable. Okay? And that's what all this bookish stuff is trying to tell you. That yes, you can do better than just the mean. Our new prediction now is not just 1 line, but 2 lines, 49.1 and 57.3. It's saying we have in the competition to explain things. Oh, I forgot the numbers again. What are the 2 predictions? 49.1 and 57.3. Help me remember that. 49.1 and 57.3. Okay. If we go over here, we can create a new line. What's one of those new lines again? 49.1?
Yep.
And we'll make it green and we'll make it thick. No, not in the shape effects. No. We can make it thick. And 57.3. And now we've created 2 lines. And those 2 lines decrease the amount by which we're off. R squared by 6.21% if we round up. Well, hang on a second. If our old prediction was just that 50Y, or what do we call it? We called it voting eligible population turnout, equals always 53.217, that was our first equation. How can we make a better equation to represent the new prediction? How would we express these contingent means in an equation? There's going to have to be some A, and there's going to have to be some Bx. Any ideas about how to put that in an equation, given that we know these two to be the averages? Anybody got any ideas?
Do you find the average of change in between the points?
No, it's simpler than that. Some of the answers are right there, right in front of you. Okay, let's go back. Let's review a bit from the beginning of class. A is the value of your dependent variable when what is true? When x equals 0. X is it a presidential election year, equals 0. So what value should A be?
Shouldn't that be 1?
Nope, not 1.
0?
When a presidential election year is 0, our best prediction is not that voter eligible turnout is 1. Our best
0?
prediction, no, it's not that voter eligible population is 0. It's what?
49.127?
7.5, yeah. Or 49.128 or 49.13 if you round, right? It's this number. Because we know that the mean of voter eligible population turnout is 49.127 when the is it a presidential election year equals 0. And that's what A is. So we're saying, hey, if it is a presidential election, if it is not a presidential election year, voter turnout is going to be 49.127. And what if it is? How do we then get the equation to say, but wait, if it is a presidential election year, okay, there's going to be some x there, and our x is the value of pres. When pres equals 1, what are we going to put in that spot to make the whole equation turn out to be 57.306?
Do we find the difference?
Yes. What is the difference between these two? How do you move from 49.1 to 57.3? The answer is find the difference. So let's take B120, which is that number, and subtract B119, which is that number. Oh, it turns out the difference is 8.179. Okay, so that's literally, if we head back over here, it's saying, look, let's add 8.179 times the value of pres. And let's make this, there we go. So we are back to where we started off the class with this piece over here. And let's just look at it a bit. What this equation tells us to do is to look at the value of pres. And when the value of pres is 0, we just take that whole 8.19 thing out, because anything times 0 is 0. And so all that we're left with is 49.127. Oh, wait. Then, if pres equals 1, anything times 1 is itself, right? So if pres equals 1, we'll add 8.179 times 1, which is 8.179, to 49.127, and it'll turn into 57.306. And actually, that equation, if you plotted it in a chart, would look exactly like that. 2 lines. One for if it's a presidential election year, up here in orange, and one in green if it's not. And that is what multiple regression is all about. It's turning our predictions into an equation that tells us what the predicted value is if we plug in different values of the independent variable. That's what this is. It's like all this stuff, all these massive, lines of data and contingent means and all that stuff, all these cells boil down to two pieces of information. First, an equation that tells you what VEP turnout is going to be based on different values of pres, which we know the two possibilities are 0 and 1, right? Because that's what it is in our data. And second, the R-squared, which tells you, if you multiply it by 100, the percent of the error that you take away by introducing your independent variable. All that work turns into these two numbers, or, well, an equation and a number. And that tells you everything you need to know about this prediction. How much better the prediction is than just saying, hey, how about the mean? And exactly what we predict the values to be. And that is what multiple regression is. In fact, I can tell you, okay, here's what we're going to try to do. We are now going to run in Microsoft Excel. We are going to take these values over here. We're going to open up a new sheet, okay, just to clarify. I'm going to run a multiple regression, and we're going to see what the actual values are. And we're going to see if all these calculations turned out correctly. We're going to let the computer do it, okay? So there's our year in VEP turnout. Let's go get the presidential election year data, okay? And let's bring it over here. And then let's there we go. Okay, so now we've just got our nice clean data. It's just like it was at the beginning. Let's run a regression. And let's do it in which, okay. You ready? Let's do this. To do this, we're going to go to data, and I'm going to show you how to run a multiple regression in Excel. Okay? Then you go to data analysis, under the data tab all the way over on the right, and then you click under options, oh, regression. What could be simpler? Then, oh look, we've got y's and x's. That's great. We know what y is. It's our dependent variable. Let's select that range. And I'm doing that, just to clarify, by clicking this little tiny weird red button, which just means, hey, go find a range for me. And then let's go find the range for the x. And that says input x range. It's awfully small. I can't make it any bigger, but that's what it says. And I'm going to click that little button to select that range too. And notice when I'm doing that I am selecting the label up at the top. Okay, I did that. So I need to click the little box that says, hey, there are labels in there. Okay? And then we're going to put the output. It's going to give us a regression analysis. Hooray! The output ply is going to be called regression, and I'm going to call it regress pres. So I remember what the independent variable was. Are we ready to hit OK and see what happens? Everybody ready? Give me a thumbs up if you're ready. Okay, I'm ready. Here we find out if I got my arithmetic right. And I don't know. Let's find out. Let's see. Are the predictions the same? Oh my word. Look at that. Wait, you can't see it because it's too small. So let's make it bigger. Bigger, 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 bigger. I was at a presentation today at noon, and the numbers were so small, and the words were so small, I couldn't see any of it. So let me make this really big. Really big. Big. I'm so excited if you couldn't figure this out. This is where the rubber hits the road. Oh, look at that R squared. 0.621, 0.06, or 6.0206, which means that yes, 6.21%, if you multiply that by 100, is the amount that we got better. The R squared, it turned out the same. Okay, and look at these. These are the coefficients. It's giving us the intercept, which is the same thing as A, and it's giving us the coefficient, the slope coefficient, for the variable pres, which is B. Yes! It is telling us that VEP turnout equals 49.127 la 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 128 plus 8.179 la 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 8.18, essentially 179 times pres. That is what these coefficients tell us. And look at that. We did it by hand, but you can do it really quick by computer. And it's the same. And I'm happy because it meant that I didn't make an arithmetic error, but I'm happy for another reason too. Okay, and I'm going to take a pause here and reflect. The reason I'm really happy is that I want to say we went step by step through a few ideas. We said we can come up with a prediction, we can figure how much it is off from the observed reality, then we can square it so that we get magnitude, and we can add that all up. We can see how far off our prediction is. Then we can come up with contingent means, right? So we did that over here. Then we can come up with contingent means, which we did by eyeball, right? By going through the data and getting averages for when pres equals 1 and when pres equals 0. Okay, and here are our contingent means. And we can get some squared error for that. We can compare our predictions, see how much better the amount of error is for our new prediction compared to our old prediction based on the mean. We can compare them, see how much they're different. They're different by 6.21%. That is the percentage of the error that was removed, which is the reverse of the amount of the error that's still there. You add those two and they add up to 100%. We can express that in an equation. Whew. And we can do all that work that took about an hour in about 10 seconds, and we get the same numbers for the equation and the R squared. Okay? So, we're still just talking person to person. You didn't see all of that, but we did see that a minute ago. So takeaway, why does that matter? Well, imagine, since I've shown you that it can work based on just basic ideas about finding the amount by which your prediction is off and things like that, and you guys followed that general idea, we did it with a data set that was pretty simple actually, right? There we are, we're back. I mean, this data set here, it's two variables that we're working with right now, column B and column C. And how many cases? 117. Oh, actually 116 if we take the labels away. 116 observations. That's pretty simple. It's a pretty simple picture. But imagine that you were dealing with a situation in which you had, I don't know, like 10,000 cases and 10,000 individual values of a variable. It'd be a lot harder for you to do this same thing by hand. But you could do it with a regression analysis, and it tells you the same thing. And that's the value of what regression analysis can tell you. And if you can get the general logic of it, you can use this just about anywhere. And actually it's used to figure out all kinds of things that you can predict. The effectiveness of a drug, or the dangerousness of a vaccine, or all kinds of things that can save someone's life or ruin their life. That's what the power of this is.